Hello, and welcome to the second video for section 10.2 on Calculus with Parametric Curves. In this video, we briefly discuss three standard geometric applications: areas, arc length, and surface area of a surface of revolution. Let us begin with computing the area under a parametric curve. Recall that the area underneath the curve y equal to f of x from a to b is given by a equals the integral from a to b of f of x dx, which equals the integral from a to b of y dx. For the case of a parametric curve, we have that x equals f of t and y equals g of t, and alpha is less than or equal to t, which is less than or equal to beta, where x equals a when t equals alpha, and x equals b when t equal to beta. We also have that dx dt equals f prime of t, or that dx equals f prime of t dt. Substituting this information into the above integral, we obtain our desired formula. A is equal to the integral from a to b of y dx, which equals the integral from alpha to beta of g of t times f prime of t dt. As before, consider the curve x equal to f of t, which equals sine of t, and y equal g of t, which equals sine squared of t. Recall that these parametric equations trace out the piece of the parabola y equal to x squared from negative 1, 1 to 1, 1. Let us compute the area underneath the piece of the parabola from 0, 0 to 1, 1. So 0 is less than or equal to x, which is less than or equal to 1, and this happens when 0 is less than or equal to t, which is less than or equal to pi over 2. Therefore, a, which is the integral from alpha to beta of g of t f prime of t dt, equals the integral from 0 to pi over 2 of sine squared of t times cosine of t dt, which equals 1/3 sine cubed of t evaluated from 0 to pi over 2, which equals 1/3 sine cubed of pi over 2 minus 1/3 times sine cubed of 0, which equals 1/3. Of course, we could have computed this area using the integral a equals the integral from 0 to 1 of x squared dx. We conclude this section by discussing arc length and surface area of a surface of revolution. We recall the relevant formulas. Suppose that you are given a curve C with equation y equal to h of x, where a is less than or equal to x, which is less than or equal to b. Then the arc length of the curve is computed as the integral L equals the integral from a to b ds, where ds equal to the square root of dx squared plus dy squared is the arc length element. Now suppose that C is given by parametric equations x equal to f of t and y equal to g of t. Then dx equals f prime of t dt, and dy equals g prime of t dt. Thus, we can rewrite the arc length element as ds equals the square root of dx squared plus dy squared, which equals the square root of f prime of t dt squared plus g prime of t dt squared, which equals the square root of f prime of t squared plus g prime of t squared times dt squared, which equals the square root of f prime of t squared plus g prime of t squared dt. As dx dt equals f prime of t and dy dt equals g prime of t, the equation becomes ds equals the square root of dx dt squared plus dy dt squared times dt. Therefore, the formula for the arc length of a parametric curve when alpha is less than or equal to t, which is less than or equal to beta, is given by L equals the integral from a to b of ds, which equals the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. Now suppose you rotate the curve C with equation y equal to h of x, where a is less than or equal to x is less than or equal to b, about the x-axis to obtain a surface of revolution. Recall the formula to compute the area of this surface of revolution. S is equal to the integral from a to b of 2 pi y ds. Now suppose C is given by parametric equations x equal to f of t and y equal to g of t, and alpha is less than or equal to t, which is less than or equal to beta. Then, using our above computation, ds equal to the square root of dx dt squared plus dy dt squared dt, we can rewrite our surface area integral as s is equal to the integral from a to b of 2 pi y ds, which equals the integral from alpha to beta of 2 pi y times the square root of dx dt squared plus dy dt squared dt. Let's do an example. Suppose that x equals t and y equals t squared, where 0 is less than or equal to t is less than or equal to 1. Set up an arc length integral and a surface area integral computing the area of the surface obtained by rotating the curve about the y-axis. Note that this is just a different parametrization for the arc length of the parabola y equal to x squared from negative 1, 1 to 1, 1. We have that dx dt equals 1 and dy dt equals 2t. So here are our two integrals. For arc length, we get that L is equal to the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt, which equals the integral from 0 to 1 of the square root of 1 plus 2t squared dt. And for surface area, we get that S equals the integral from alpha to beta of 2 pi y times the square root of dx dt squared plus dy dt squared dt, which equals the integral from 0 to 1 of 2 pi t squared times the square root of 1 plus 2t squared dt.